All right, welcome to some new slides. The topic today is pointers, which is a fun one. It'll help us learn a bit about how memory is arranged inside of our programs. So it is a very important topic, but it's also a very difficult topic. It's one of the hardest in this class, I'd say. So definitely pay a little bit of extra attention. I'll be here to help, though. Ask me lots of questions. There's also this nice resource, this little file from Stanford. It's a good resource if you want to read more. Of course, you'll be reading about it in your book as well, but it's a hard topic, so it's good to see it from a bunch of different perspectives. So yeah, some fun stuff today. I guess I should motivate the topic. If it's so hard, like, why do we need to know it? Well, to learn pointers, it's going to help you, when you learn pointers, it's going to help you understand what's going on in your programs as they're running, like how the memory is actually arranged and how things are moving around. That will help you understand, like, why bugs happen, why certain classes of bugs occur in your programs, and also it will help you just like understand your machine better that you're programming on, so you'll make faster programs and they'll just be all around better. All right, so I guess that's my motivation for you. If nothing else, you'll be able to understand this this silly little comic by the end of today's class. So there. All right. So yeah, let's talk about first what memory looks like under the hood when you open up your computer. And so by memory, I do mean RAM, random access memory. So that's the piece inside of your computer that's storing stuff as your programs are running. And your programs themselves are getting copied into RAM, remember, when you run them. So here's some new words, some new ideas. All right, so secretly, deep down, your computer's memory, it's really just a giant table. It's just an array, really. And what it does is it takes the indices, which we call addresses. It maps those addresses, which are usually large numbers, 64-bit numbers on a 64-bit processor, and at each address, which is just an index in this giant array that is your memory, you can get out a byte of information, so an 8-bit number. So every address is mapping to a single byte, and so that is what memory looks like. It's just a big long table, all right? And this is secretly what's there. So you got a bunch of things called addresses, which are just the indices of your array that is your memory. And at each address, you can store a single byte value. Okay, so here is a zoomed in picture of what memory might look like. So the very first address is 0, of course, and then you can store a byte there. Then the next address is the address 1, you can store another byte there. Next address is 2, next address is 3, you can store a bunch of stuff there, and there's plenty more on down the line, right? So at address 0, you can store like 42. At address 1, you can store 43. And you can play around with this as much as you'd like. You can just put a bunch of data there. All right, so you can send data to those addresses. The addresses are just like the indices. It's like the mailbox. It's where you go. So like at address 0, shove that value there. Put 42 there. At address 1, put 43 there, please. Like send that mail to them, and like that fills up their mailbox. And so like you can put data into an address, and you can also get the values back. So like, all right, I want to put 33 into address 2, and then maybe I want to come along later and be like, all right, what's in address 2? Okay, 33, let me add 1 to that and then store it back. So like you can retrieve the values just like an array, just like a normal array. You can put 34 at address 3, and then eventually you can put something different. You can rewrite it, that's fine. The largest byte value is 255, by the way. So that's not as big as you can put in a certain address. So yeah, 64-bit numbers are your addresses, big, large numbers potentially. Lots of options. And that maps to 8-bit numbers, each byte value at each address. All right, so that's what memory looks like. And everything that you could ever want to put inside of your program, every piece of data, even your code itself, it's all there. It's all somewhere in memory, which means it has an address. It may take up multiple addresses, and so we tend to consider things that we store in terms of where they begin, because they might take up a bunch of contiguous memory. So we like to think about what's the address where this data begins, because it might take up multiple bytes. All right, so we think of it that way. That's what memory looks like. All right, and so that kind of gives away this answer. Like, how do we store things that aren't numbers or things that are larger than a byte? Like ints, for example. Ints are large. How do we put those in memory if we can only put a byte per address? How do I store a 4-byte thing? Well, they're just going to take up 4 bytes in order. All right, that's what I meant by starting address. So yeah, here, let's say this. When you say int x equals 42 now, my favorite line to give in this class, I guess, that I've been drawing it like this, right? It makes a box in memory called X, it holds 42. But really, now that we know that there's a concept of addresses and like starting addresses, there's more information here, right? This doesn't really look like this. Let's say that X got the address, like it lives at address 16. That's its starting address, we say. And so if we knew that, what does memory really look like now? You got your addresses and your values. You go on down to address 16, and that's where this X is going to start. So you can store a byte at address 16, and every int is 4 bytes long, though. So that means it's going to take up contiguous memory up to address 19. Does that make sense? So if an int is 4 bytes long, it's taken up 4 things starting at the starting address. So it's taken up, if we have an int that starts at address 16, it's going to take up addresses 16, 17, 18, and 19. Does that make sense? That's the secret. All right. And so somehow we're going to use those bytes to store the number 42. So like that's what it really is going to look like in memory. All right. And so 16 is the starting address of X. That's where it begins. So where the int X starts. Okay, I hope that makes a little bit of sense. That's secretly what's going on in memory. That's what it really looks like. Okay, yeah, and that's, I think, all that I want to say. There's plenty more addresses where you can have more stuff, of course. And non-numbers, remember that we can always translate stuff into numbers. Everything's ones and zeros at the end of the day. So like doubles, those are numbers, but they're stored in a weird way, but they're still binary. Still a bunch of ones and zeros that represent your 3.14 or whatever. And then strings, we know those are made up of individual characters, like an array of characters. And characters are just a bunch of numbers because we have ASCII values per character, don't we? Some character is the number 42 secretly, all right? So yeah, that's how we can store anything in memory. And there's always a concept of a starting address because a lot of the things, like ints, they take up multiple addresses, not just a single byte, but 4 bytes for ints, 8 bytes for doubles, etc., etc. Okay, so we're eventually going to start talking about these giant addresses, and these can be huge numbers. They don't have to be small like this. And I have like 64-bit numbers, which are very large, 64 ones and zeros to store, to talk about where things are stored inside of our computers. So I need to teach you a different kind of number system now, because instead of printing addresses as 64-bit binary values, like 64 ones and zeros, that's way too much work. The computer's going to print them in a different base called hexadecimal, all right? So instead of printing your binary numbers like this, a bunch of like 64 ones and zeros, C++ is smarter than that. They print addresses in what's called hexadecimal, or hex for short. And it's a different base. It's not base 2, it's base 16. It's still a power of 2. And so that allows there to be a nice correspondence between binary values and hexadecimal values, hex for short. So it comes from the Greek roots for 6 and 10, right? So 16, it's base 16. And so to make base 16 numbers, you need 16 digits before you add a new place, don't you? We have 10 from our normal number system, but we need even more now. We need a single digit that represents the idea of 10 in hexadecimal, don't we? And so we're going to start using letters for that. So A. A means 10 in hexadecimal. B means 11. C means 12. D is 13. E is 14. And F is 15. So that is the largest single digit you can have in hexadecimal. That's pretty cool. So you can go up to 15 before you need another place. So like F then. Let's do some hexadecimal math. F plus 1 in base 16 land, there's your 1, 0. That's the number 16. 15 plus 1. All right? I hope that makes sense. So that's kind of cool. And your computer is going to print out addresses in base 16. It's going to print out addresses in hex instead of big, long binary numbers. That's good for us. It's hard to do these subscripts in computer land in a terminal. We can't really do that very easily. And so your computer will print it out with a 0x at the start. That just means, like, interpret what I put next after this 0x as a hexadecimal number. That's its version of doing the subscript, which you can't really do on the terminal. All right? So that's useful because, like, you don't know if you see 1, 0, is it the number 10 or is it the number 16? If you saw this, you know it's the number 16, right? You know that it's in hex. That's why it does that. And all right, let's figure out what is this in decimal then. Let's do the translation. You know how to do that, right? So here, well, this is going to be A times 16 to the 0 plus 3 times 16 to the 1. What is that? Well, that's definitely 3 times 16 plus A, but what's A? It's 10, yeah? Plus 10. And so I did the math ahead of time. That is apparently 58. All right, 58 in decimal is what that represents. So the numbers in hex look a little bit smaller than what they really are, because like you have more room per digit. Interesting. So yeah, the reason C++ prints out binary numbers in hex instead of in binary is because there's a nice correspondence. For example, every byte value looks like this in hexadecimal. It goes from 00 to FF. You only need 2 hex digits to represent 8 bits, if that makes sense. So like this is the smallest byte value, this is the largest byte value, and that's super useful. So every 2 hexadecimal digits corresponds to 1 byte. So when it wants to print out addresses to you, it's going to show you, let's see, instead of 64 ones and zeros, it's going to print 8 bytes worth of information. That's 64 bits, right? So that's only 12 hex digits. That's much better. And in reality, it'll be even shorter than that. So that's why we need it. This is a new number system, and yeah, I'll show you that in a second. So okay, let's understand this table some more now. So like this is what really is going on in memory when you make ints. Let's talk about that a little bit more, and then I'll actually talk about the topic for today. So okay, let's say that we run these 3 lines in code. All right, so I've been drawing it like this. All right, the first line is like, all right, int x equals 42. We need to go further than this now. Y is going to hold 43, and then int z equals y. We know what that means. It makes a brand new box z in memory, and it just copies in whatever was in y, doesn't it? So it's like, all right, the 43 is going here now too. But really now, what do we know? In addition to that, they make the boxes in memory, but we have new ideas, right? First of all, we have to understand that they're all separate boxes. We understand that, right? These are not, even though these 2 hold the same value, they're different boxes in memory. They're different places, different variables. And because of that, they have different addresses where they begin, don't they? And these 2, if you think about it, they mean the same thing. So now we know, like, inside of your computer, it doesn't know what x is, y is, z is. It knows about addresses where things start. We as humans say x, but it's like the thing that starts at address 4, that's an int long. That's 4 bytes long. And then let's say they go in order, like y can start at address 8 because x is going to take up 4, 5, 6, and 7, right? Because it's going to be 4 bytes long if it's an int. That means z can start at address 12 if we want to put them in order like this. So that might be where the compiler puts them. So yeah, humans use variable names. Computers are using addresses. That's what the computer is going to be referencing and figuring out, like where things are in memory. That's how it's going to places. And so if we draw our big long table of addresses to values, what does it really look like now, given those example addresses? How does x, y, and z look in memory? Well, if x starts at address 4, that means it's going to take up, starting the 4 bytes, right, at addresses 4, 5, 6, and 7. That's x. That's where it lives. And then 8, 9, 10, and 11 make up y, and then 12, 13, 14, 15 make up z, ... You can have more things after that. But this is where x starts. That's going to take up those 4 addresses and somehow hold 42 there. We'll talk about how eventually. And then y is going to take up those addresses and hold 43. And then z starts here. It's always a concept of a starting address, the smallest address where the memory is beginning. And z will take up those 4 addresses and hold also 43. They're 2 separate places in memory, though, even though they hold the same value. All right? So yeah, understand this correspondence. That's important. And I think we are now ready for an example. This is mostly just review, honestly. This question is a review, but it gets into the idea of memory some more. Well, I want to talk about it in terms of what we understand about memory now. So all right, here's a silly program that there's something wrong with it. Pretend like there's IOStream and stuff above, but like here's the main program. And so let's pretend like we make an age variable we call birthday on age, and then we print out age again. This is the birthday function. It's meant to like increment things, right? And so what is going to be printed? What do you think? Pause the video, run the code in your mind. It's not what you expect, right? This is call by value, so it's going to just copy things, right? So this A is a separate A than this age. There's no references, no nothing like that. You remember it now? So there's that. Let's see, do I want to go to code for that at all? Not really. All right, so we understand this. This is a review, right? But let's zoom in on the memory now. We can talk about it in a different way. So like here's the main function calling the birthday function, and so main makes this age variable, and so it has an address. It has an address, and it's going to store 19. All right, so we did that. That's what the memory is going to look like. And then we call the birthday function from main, and it's going to pass along to make a brand new variable. Its local variable is called a. All your parameters, if they're just normal ints, it's a brand new place in memory. Do you see how it's having a different address? And that's going to be, we're going to copy age into a. So it will hold 19. And then it's messing with a, and then it returns, but it didn't really mess with age because it was a separate place. Like the a equals a plus 1 does that. But then birthday returns and all of its memory goes away. So like this address had nothing to do with this address. There were different places, different ints. Oh no. Do you see it? So that's just review, but now we can talk about addresses. That's interesting. There are different places in memory. They have different addresses. And we know how to solve this problem. We can use references. We can put a little ampersand here, and now suddenly these two have the same name. It's the same box, really. But there's something different that we can talk about as well. References are secretly using this concept called pointers, which is more lower level. So references is kind of using this new thing called pointers that I'm about to teach to you, and like making your life easier. But I want to teach you the secret. I want you to understand the lowest level pointers so that there's no magic to you. All right, I want you to understand it in total so that you know exactly what's happening in memory. So references are secretly using pointers, so we better learn pointers. How are things really working at the lowest level? Let's do it ourselves. All right. So here is a very important slide. So what a pointer is, what I've been trying to get to is this slide. A pointer is just another variable. It's just another box in memory, but what it holds is special. A pointer is a variable that can hold on to the address of some other variable. That's interesting. A pointer is a variable that holds the address of another variable. It can't hold its own address unless you do something really weird. So think of it as the address of another variable, okay? So we say that a pointer points to that variable when it holds its address. Like it knows its address. It knows how to get to it. It has a map or something. Okay, so to make a pointer, here's how you create one. It's just another variable, but it has a fancy type. So you say the type of the thing you want to hold the address of, like int. I want to hold an int's address. I'll say int here, and then you put a star. So not an ampersand, but a star, and that makes the full type. So that makes a pointer to that original type, and then you give it a name like a normal variable. And you can put the star anywhere. It could be closer to the type. Could be closer to the name of the variable. Just like for references, you can put it anywhere, it doesn't matter. I'll try to put it next to the type because I think of it as one big type. It's like a type modifier, all right? And so that means that pointers are type specific. If you want to hold the address of an int, you got to put the name int here, int star, all right? So that's this example. So if I want to hold the address of an int eventually, here is a pointer that can hold it. It's going to be an int star. Does that kind of make sense? That's the type of it. That's the full type of it. And you kind of read it backwards. P is a pointer to an int. It's capable of holding addresses of integers. It itself is just another box in memory, though. So like P, here's P. It's holding garbage. It's holding the garbage address right now, I guess. But it also has a place in memory where it lives. It has its own address. But what we can put in here is other people's addresses. All right. If we're not ready with an address yet, like we don't have an int to put in here, like we don't have the address of another int to put into P yet, then you can store a special default value called the null pointer. This is a special unused address, and in our programs it's actually the address 0. So I was a liar when I said that we could store stuff at the 0 address. We actually can't. We've all given up that address, so that it means error, like it's unused. It's an address that we can't access. So we've given up the 0 address to mean the null pointer, and you can't actually look at that address in memory in your programs. So that's what a pointer is. Do I want to show you anything about this yet? Yeah, let's write some code. All right, we'll fill it in with more stuff soon, but let's at least get started. Pointers. So here, int star p. There it is. So I made a pointer. So p is a pointer to an integer. It can hold addresses of ints. All right, that's what it's capable of doing. And right now it's set to some garbage address, but let me at least show you how it's going to be printed out. It's going to be printed as hexadecimal. So my garbage address right now, what is it holding? It'll change every time probably. There it is. There's my garbage address that's held in this pointer p. So I should never go to this address because it's probably something I don't have access to. But like that's what it's going to look like when it prints it out to you. It's nice and hexadecimal. And of course it's random, it's garbage. So there's that. If you're not ready with something, you can give it the null pointer. So you can say give it the 0 address. P equals null pointer. And at least then it's like initialized to something that'll actually give you an error if you try to go to it. Is null pointer is a special, it's an unused address. And it is the 0 address. So that'll print as 0 now. Okay? That's a good default value when you're not ready with the address of an int yet. Okay? So, all right, let's say we do make an int. How do we give that address into our p variable? How do we have it hold on to it? There's some new syntax. All right, so let's get started first though with let's make an int and a pointer. So let's do this. Let's actually make an int x equals 5 that has a starting address. All right, and it holds the number 5 inside of it. And then let's make a pointer to an int p. All right. And then it's going to start as garbage because I haven't given an initial value. But my goal is to store in p the address of x. That right there, that 100 in hex. Does that make sense? That's what I'd like to do. That's what I want to have happen in memory. And so all right, we can make our x. Let's get it ready. I have an int x equals 5. I want to eventually put the address of this x into the p variable. That's what it's capable of holding. And so here's how you do it. It's new syntax. I'm so sorry because it's using the ampersand again. So you've seen the ampersand in so many places. Here's a new place where you can use it in a different way. When you say ampersand outside of a type, because inside of a type it means reference. When you use it outside of a type in an expression, it's called the address of operator. So you have the ampersand, you give the name of a variable, and it gives you the address in memory where that variable lives. All right, that's what it gives back to you. So you read this line right here, or this part of the line, as address of x. All right, it's the address of operator. All right, so that's what's going on. And if you do this, then this will turn into the 100. It will get it, 100, sorry, it's in hexadecimal, maybe. It'll get the 100, that will evaluate to that, and it will shove it into p. And so it will store 100 into p, and then we say that p points to x because it knows where it lives, right? It has its address, it can get to it, and we draw it with an arrow like that. That's why we call them pointers. P is pointing to x. It's a way of indirectly getting to x. It knows how to get there eventually. All right. So that's that. Let me show you that in code. So let's store this. Let p hold the address of x, please, and then here I'll print p. So now p holds whatever the address of x was, and so when I print p now, it's the address of wherever that x variable was in memory for my current program. So it just so happens to be this one. That's the address of x in memory for this run of the program. The program gets loaded into a different place in memory each time, and so this will change every time I rerun the program. It doesn't have to, but it most likely will. It's just that's the address of where the x lives right now. This memory I can access if I want to, but I need to show you some more syntax to do that too. All right, so I actually have a question for you. I want you to discover it. So I'm so sorry, again, we're overloading something. The star operator. So we use the ampersand to get the address of something. We use the star in a type to make a pointer. If you use the star outside of a type in a fancy way like this, it is called the dereference operator, and it's meant to follow the pointer. All right, so my question for you is what is this actually going to do? Can you extrapolate what's going to happen here? What is this code going to do? If we've set up memory just like this, p is pointing to x, p lives at this address, it holds, though, this address. It's pointing to this box right here. X's address is 100. It holds the number 5. What do you think will happen when you say cout star p? Pause the video and think about it. What do you think that following a pointer should do for you? Do you see it? Well, let's discover it together. If I say cout star p, what is going to happen? I get 5. Is that what you expected? That is it. That's what it does. It's going to follow the pointer, go to address 100, and look at the thing in the box. It doesn't go to the address. It gets the thing in the box. Right? So the answer is B. Does that make sense? So the reason these two aren't the answer is because you can get at those in other ways. So how do you get the 104? That's the address of P, isn't it? So you could have gotten that by just saying this, cout address of P, right? That's not useful. And then how do you get the 100 otherwise? There's already a way to do that. That's just cout P by itself, whatever P holds. That's the address. But to go to the address that P is pointing to, That's what dereference means. All right, it follows the pointer. Does that make sense? So for all intents and purposes, star p, whenever you say it, because like p is holding the address of x, star p goes to this box and it gives you whatever x holds. It's essentially a synonym for x. Star p is a synonym for x. So you kind of see where references are coming from now. Like it's doing all this for you secretly under the hood. This is what references do for you secretly, making pointers, following pointers for you. All right, so that's the dereference operator. It follows your pointer. Okay, and so yeah, that lets you access your memory in a roundabout way. It's indirect. All right, so dereferencing a pointer gives you the value of the thing it's pointing to. Another name for that is the pointee, right? The pointer is pointing to the pointee, the thing being pointed to. And yeah, it's just giving the contents of that box in memory. So they let you get stuff out and even modify your variables, your other boxes, indirectly using pointers, using the star, indirection, dereference. So like if this was your memory again, x and p, x lives at address 100, p lives at address 104, p holds the address 100, so it's pointing to x, which holds 5 right now. If you said this will let you change the value. So star p equals 6. Star p, for all intents and purposes, is giving you this box. It's as if you said x. So this line is as if you said x equals 6. Does that kind of make sense? That'll set this box just like that. And then star p equals star p plus 1 does also what you would expect. So first it calculates this. Star p plus 1 is, all right, 6 plus 1 is 7. Where am I storing that into star p? Where is that in memory? It's this box. See it? That is going to make 7 here. And that's as if you said x equals x plus 1. So like star p and x are synonyms right now because p is pointing to x, if that makes sense. So yeah, do yell at me, ask me lots of questions. This is interesting stuff for sure. So here, star p equals star p plus 1, and then if you print star p, you'll get your 6 out, but also x. X and star p are the same because p is pointing to x. It's holding its address. Can I show you everything? I can. Cool. There it is. There's just 2 ways. You have options now. You can go through p to get to the value indirectly, or you can just like say x if you have that visible to you right now. So the beauty of pointers is, again, across function calls or method calls, because now you have another way of getting at somebody else's memory, don't you? You could pass along an address, and that's a way to get to some place that maybe isn't yours. So here's like the answer to the birthday problem. Without using references, you can use pointers instead. See that? So here's the secret. Here's what's going on. Here's what you could do. You'll just like change it to use pointers up here, and like you're passing along an int pointer, and you're messing with the value that it's pointing to. See, it's incrementing it that way. And then when you call birthday, you don't pass along the age itself. You pass along the address of where it is in memory, and that lets you, through a now, which is a pointer, get to that stuff. Does that make sense? It's like here's what the stack will look like. You make age, you call birthday, which has its own variable. A is still its own separate local variable, but it's a pointer. It's a pointer that can hold the address of some other int. So it's going to hold that 100 here, and by saying star a equals star a plus 1, we're messing with this box now. Do you see it? Beautiful. And so secretly, this is what references are doing for you. It's secretly using pointers. So I kind of lied when I said it's not actually using any memory, because it's using a tiny amount of memory, just 64 bits to store the address. So that's much, much less than like your size 1 million vector that you would have been copying otherwise. So for all intents and purposes, it wasn't really using much memory, or any at all. So yeah, that's one way to fix this problem. And when you use pointers as parameters, instead of call by value, which was just copying, call by reference, which was using references, we call this one call by pointer or call by address. All right, so let me write that in code. Oops. Call by address. Just so that you have it. It's can I copy all of this? That would be very nice if I could. Boop. And it messed with the space values for no good reason. So let me substitute that weird space value with a normal space value, and I think it's happy now. There. And so usually, so you can put the star next to the variable or next to the type. It does not matter. So yeah, there's the birthday function. It's going to work this time. It's another way. And this is call by address or call by pointer parameter passing, because we're passing along a address of somebody. Okay, and so it does make 20 in age there. Beautiful. All right. Yeah, so now you can have variables, you have boxes of memory, and arrows to those boxes. You can make pointers to other places. Okay? And so one day you might come up with you might have like a jumbled mess like this, especially on a test. It might be something that I give you. Do you see how you could parse this? Like what's going on? How are all the different like variables interacting with each other right now? So let's see. Yeah, if I gave you this is a pointer diagram. If I gave you this, how could you, do you see how like all the different ways that you could change this box from 5 to something else? Change it to 6 or something? Because like P is pointing to X, Q is pointing to X, and then you have a pointer to a pointer. R is pointing to Q, which is pointing to X. Do you see it? That's a little interesting. So like, all right, if the original variable is X and it's an int, then how can we change it? We should be able to use all these other pointers to change it. Does that make sense? So like you could have said X, but you have options now because like P is holding the address of X, Q is holding the address of X, and R is holding the address of Q, which is holding the address of X. So there's a bunch of indirection going on there. It's like X equals 6 will do it. You could have also said star P, right? Follow, go to that address, get to this box, mess with it. Star P equals 6 could have worked. You see it? And Q is exactly the same. Star Q equals 6 would have done it as well. Sorry, star Q. And then what about R? Could you use R to get to X somehow? Because if you said star R, that gets you to this box. It gets you the 100, doesn't it? And that's just another pointer. Do you see how you could follow it again? Go to address 100 now. Star star R gets you to here. Do you see it? Equals 6. That would work. Isn't that weird? That's kind of interesting. So yeah, you can have pointers to pointers. That is totally fine. You can dereference twice to get there. A good rule to remember is if you want to get to here from here, you have to use a star for as many arrows as there are. You have to follow them because every star follows an arrow. See it? So I think that's what I wanted to say there. And then alternatively, what if I gave you this diagram? Like, could you make it? Could you make it in memory? Could you code this up and create this this way of memory? If I gave you the diagram, could you create this in code? Create this setup. So, all right. What does that mean the types of the variables are? Assuming that X is an int. We know that assume that X is an int. Like, what are the types of all these other things? So let's think about it, and then we'll put it into code. So I'm going to use this kind of syntax, by the way. This is something that you'll see eventually. It's if you say the name of a variable and you put a colon, it just means the thing after the colon is the type of that variable. That's just a fancy way of doing that. So X's type is int. So the type of X is int. That's how you read that. And so, all right, what are P and Q? What do they have to be, right? What are P and Q? If they're holding the address of an int variable, what must their type be? We've done this already. It must be this, right? Int star. Does that make sense to you? P's type must be int star. Type of P must be int star. Same with Q. And then why though? Why? If you think about it, whenever you use the address of operator, that's going to give you the address of whatever you had. So if you said ampersand X, it will give you back the address of X. It'll give you the 100. What is the type of that 100? Well, it's the address of an int. It's an int star. Whenever you use an ampersand, it kind of tacks along a star to the original type of the thing. See it? So with that in mind, now we can do more. So like Q for sure has to be an int star, doesn't it? Has to be an int star. And so like here's the setup. Like it would have been int X, int star P, int star Q. And then what about R? How would you make R? Well, R has to hold the address of Q, doesn't it? And so what is going into R but the address of Q? So we're going to do ampersand Q somewhere, aren't we? Well, it must be the address of Q. What's the type of that? Well, it gives back 150. What is the type of that? Well, following this pattern, just like, all right, it is the type of Q with another star. It's a pointer to a pointer. It's an int star star. You see it? Because Q is going to be, R is going to be a pointer to Q. It's going to be a pointer to an int star. That's how you read it. See that? Just like you tacked along another star. That'll work. So it's got to be int star star. And that doesn't look very pretty. Int star star R. And you read it like this, like it always means it backwards, right? R is a pointer to an int star. It's capable of holding addresses of int stars, and that's exactly what we need because Q is an int star. Do you see it? That's how you think about it. And then you can go further. You can go all day long with this. Like you can make a Z variable that holds the address of R. And what must the type of Z be then? Well, if R is an int star star, Z's type better be an int star star star, huh? Because it's a pointer to an int star star, because that's the type of R. That's how you think about it. It's very weird, it's disgusting, but that is how it works. Okay, so let's code this up in memory now. We have the values, we have the ideas. We have no control over like where the variables are made in memory, but we can at least make the diagram. We can make the setup like P can point to X, Q can point to wherever they live, and then R can point to Q, Z can point to R. We can set that up. Okay, let's do that. Let us do that. So here, let me like section this off with a new line. Let's take stock of what we have. So we've already got an X and a P, and P is already pointing to X. So we've already done that part. Let's do the rest. Let's do the Q and the R and the Z. All right. So we've got what do we need here? Let's do Q. So int star Q, right? And then what does it hold? It also is going to hold the address of X. So ampersand X. Ampersand X. Alternatively, because P already holds the address of X, I could have just said that int star Q equals whatever P holds right now, because it's just the same thing. Copy and so you could have said equals P, if that makes sense. All right, what about the rest? So int, it's going to be int star star R, and it's going to hold the address of, I forgot a space. It's the wrong place to put it. It's going to hold the address of Q, right? R is going to hold 150, which is the address of Q, or whatever it really happened to be. So there's that one. And then finally, Z, int star 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 Z, because Z is going to be a pointer to an int star star. It's going to hold the address of R. Do you see it? That's how you think about it. And then now I have a million ways of getting to this 5 and potentially messing with it. I could say C at X. I could go through P or Q. I could have said star P, star Q. That'll get me the 5. I could go through R, right? Start at R and get to Q, then get to X by doing 2 stars. So it's going to be star star R, because star R gets me to Q, and then another star on top of that gets me to X. And then likewise for Z, it's going to be 3 stars, because 1 star gets me to R, another star gets me to Q, then that last star gets me finally to X. And I wanted to follow 3 arrows. That's how you think of it. Okay. So yeah, those are all going to print whatever the current value of X is, which I think we incremented it up here, so it'll be 6, right? So let's watch it work. Lovely. Do you see it? That is weird, but it's going to work, and that's how it is. All right, that's pointers in a nutshell. A little disgusting. You see why it's difficult, right? You have to pay attention to all these diagrams now. Lots of boxes and arrows for us today. So with that, you are getting there. You're learning pointers a little bit, and I hope it's starting to make a little bit of sense. Do yell at me if you have any questions. This does unlock another error, sadly. So you can have a new kind of issue, which potentially you've already experienced when you've like gone past the end of an array or something, because it's the same idea. Let's talk about what's called a segmentation fault, or a seg fault for short. So when you run your program, you don't get all of your 16 gigabytes of RAM or however many there is inside of your computer. Your program only gets a tiny fraction given to it from the operating system whenever you run it. So it's not getting the full amount of RAM, because like every program on my machine has to share that same RAM, right? So that means there's parts of memory, there's addresses then that don't belong to you. If you try to go to memory that is not yours, or if you try to go to the special null 0 address, which nobody has, then you get what's called a segmentation fault. You've tried to access outside of your segment of memory that's been assigned to you, and that is a runtime error, because like that's unrecoverable. Like you did a very bad thing right now. You should never have gone there. All right. So it's called a seg fault for short, and it is a runtime error. You may have experienced this already by going past the end of an array, because when you do that, you might be trying to access memory that's not part of your program. You see it? So that's it. So let me show that to you. Just a few ways of getting it. So this is segmentation fault, or seg fault for short. New kind of error. So the easiest way to get one is to have just a garbage address like int star p semicolon and like try to dereference p, because most likely that garbage address wasn't part of your program. Or if you just set it to null pointer, like nobody has access to the null pointer, that will force a runtime error upon us. There. So you see, segmentation fault, core dump, that's disgusting. That is a runtime error. You may have seen that before, but now you know why it's doing that. That's what happens when you try to go to memory that is not yours. Okay? So do not be afraid. It happens to the best of us, but now you know. All right? And I just have a few more examples for today. Let's talk about pointers versus references, because I claim that pointers are like the lower level way of doing things. References are just a wrapper around pointers, trying to be helpful for you. But now you understand the lowest thing, which is great. So let's have an example of swapping two values using pointers and using references. All right. Let's remember references first. Okay. We'll do a call by reference swapping, and then a call by address swapping, or a call by pointer. So I'll call this swap ref and pointer.cpp. So let's make int x equals 42, int y equals 43, and then I'll have two functions. I'll have a swap by ref function that swaps x and y by reference. So you'll give those values like that, and then hopefully x and y will have swapped places. So we'll print them out to see that. And so if you do a call by reference, it's just void, right? Swap by reference. It takes two things. Let's call them A and B. Not by value like this, but by reference. It's going to take a reference into A and a reference into B. It's going to rename somebody else's memory. That's perfect. And so when I pass along x and y, they're going to become A and B, and it's just new names for those places in main. And so it really will do the swapping. So if I say int temp equals A equals B equals temp, that will correctly swap x and y. This will work. There we go. So we get the 43, 42. They did change places. All right, and so let's remember how this is working. Let's draw what's going on the stack. So main makes these two variables. It makes x and y, and they held 42 and 43. Boop. And then we called swap by ref with x and y being passed into A and B. And so I need to use a different color to talk about all the things that swap by ref owns. All right, so what does it have right now? So you're passing along into int reference A x, and you're passing along into int reference B the y. And so that means A and B are just different names for the same box. That's why I needed green, right? And then the rest, temp is a local variable just to swap by ref. So temp equals A. There's temp. We create that, store A inside of that, which is 42. Then we say A equals B equals temp. So A equals B says, all right, put a 43 here, and then B equals temp. That shoves the 42 right there. And that's why, like, when this returns, it really will have worked. Right? That's swap by reference. That's how I want you to think about references, even though they're secretly using pointers for you. That's how we think about references. And so that's the diagram for that one. All right, that should be review. And now let's do a swapping by pointers, the lowest level. Let's do it ourselves. So let's make a new one. I'll call it swap by pointer. And we're gonna have to pass something different in a second. So let's make it at least. So swap by ref. It's very similar to swap by ref, but instead of taking references, it's going to take pointers to ints. And so this no longer makes sense. Like the temporary value that we want to save for a second is not A. That's an address. We want to save the int value, start A. And let's swap the values at the things that are being pointed to. So all those things. Temp is still a normal int. That's fine. But that'll work. And then when we call it, we want to pass along addresses into int star A and int star B, into the pointers A and B. I'm going to pass along the addresses of the ints that I want to mess with. So the address of x, that's the first int I want to mess with, and here's how you get to the other int I want to mess with. They're being passed along into A and B. You see that? And then that should also do the swapping. Okay? I'm sorry, this needs to be called something different. Swap by pointer. That's what I meant to call it. Now it's happy. And so that should swap them back to 42 and 43, and it does. All right, so now let's draw what's happening here to understand it fully. So okay, what was the state of the program before we got there? So swap by ref returned. Here, let me use blue again. So swap by ref returned. And so what did memory look like? We still had x and y. Let's say that we're right here in between lines. We're about to call this one. So x and y have been swapped. They are now 43 and 42. And then we go off when we call swap by pointer with x and y. All right, or with the addresses of x and y being passed along into the pointers a and b. So this was swap pointer. And so we have a bunch of local memory for swap pointer. We have int star a and int star b. Those are two boxes up here. They're just, pointers are just normal variables. They just hold special things. So we have a and b, and what they hold is the addresses of things. So let's say that x's address was 100, y's address was like 104. By passing along these things, passing along the address of x into a and the address of y into b, that means they hold this. Like a is holding 100, b is holding 104, and so we've made this pointer relationship happen. Do you see it? We have indirect ways of getting to x and y now in main. And that's what we do now. So now we say int temp equals star a, so we make a new temp integer that holds star a, so like 43. You see it? And then we say star a equals star b. That's saying, all right, set into this box whatever star b holds, which is this thing. So that's going to shove 42 right here. And then we say star b equals temp, right? That's this last line. So it's saying set star b, this box, to whatever temp holds. Do you see how it's going to do it correctly? Oh, did I mess something up? Sorry, I said star a equals star b, so I should have put 42 here. And then now it's star b equals temp, so that'll put the 43 here. There we go. And that'll do it. That fixes it. And then this returns all the a, b, and temp go away, but we made the change in main's memory. Okay? And so that's why that works. All right, I think that is what I wanted to show you there. Yeah, just yell at me if you have any questions about anything. I think the last thing that I want to show you is one new piece of syntax. There's an operator that looks like a little arrow. It's cute. And we do call it the arrow operator. So what this is for when you have classes and pointers. You can make a pointer to anything. It doesn't have to be like an int or a double. It can be an object that you point to. So like here, you can make a string s that holds something, and you can make a pointer to that string if you wanted to. So like here's a string s that holds a, b, c, d. And just like everything else, it has, like, maybe it takes up a lot of memory, but it has a starting address. Everything has a starting address, so maybe s starts at 100. You can make a pointer to a string, for sure. SP, pointer to a string. Star, string star, right? SP is a pointer to a string. You read it backwards. And so that means SP will hold, if we do it this way, it'll hold the 100, or whatever the address really was. And we have a pointer relationship just like that, all right? But SP, what is that? It's just a box of memory. It's just a number. SP is not the actual string, is it? So this doesn't make any sense. I hope you see that. Like sp.size, like 100.size, what do you want here? That doesn't make any sense. That doesn't work. If you want to do string stuff, you got to get to the string. You got to follow the pointer. Does that make sense? So you want to do string stuff, you got to follow the pointer. And for weird precedence reasons, you have to do it this way. You have to do the star p in parentheses. That'll get you to the string. And then now you're ready to do the dot size on the string. Then it's fine. Alternatively, because everybody hated that was silly, everybody decided that, all right, I don't like it this way. So they made a new operator that does the star and the dot for you. It's the arrow. So you say sp arrow size, that will also work. All right, these are two equivalent ideas. All right, so sp arrow size will just like dereference and then do the dot for you and call the size method. I hope that makes sense. So yeah, this way may make a lot more sense to you right now, but you'll grow to prefer this way because it's less typing. But just remember that you got to get to the actual string. Star sp, right? Gets to here. That's another name for s. That finally gets to the s, and then you do the dot size, and that's just equivalent to this now. Okay, so I think that's the last thing I want to show you. So here, boop, and so I'm going to use strings. I better use the string library, and then I'll make a string star, right? SP is a pointer to s. Right? It's going to hold the address of s. It's pointed to s right now, right? So remember that SP is just a number. SP.size does not make sense. It will not compile. let's see here. So I was just confused. It's like, I don't know what you want here. It's a pointer, it's just a number. Maybe you wanted to use the arrow? We did. So yeah, you have options. Now either you could say it like this. You could say, all right, give me the string. Get me to the string. That's star SP in parentheses. Now I'm at the string. Then I can do the dot size. Then it's happy. So that'll work. That'll give me my correct size. Oops. Which is 4. Alternatively, or equivalently, you could do the arrow, because nobody likes to type the shift key too much. SP arrow size does the same thing. It dereferences and does the dot for you. Oops. That one. There. Both give you 4. Okay. So yeah, you can have pointers to objects. It's totally fine. It's totally allowed. And yeah, now you know secrets of C++. You know what's happening when you use references. It's really making pointers for you and dereferencing them for you automatically. That's kind of neat. But a lot of the time, sometimes, you will want this fine-grained full control, and now you know how to get it. All right? So that's where I want to stop today. I think you can kind of understand that one now. Cool. So, okay, we'll come back and talk about more pointer stuff in the next lecture. So I'll see you then.